Hi everybody, and welcome to this course on analysis, random walks, and groups for the autumn 2020. And in this course, this lecture is just going to be like an introduction to this course and the kind of things that's going to happen in here. And it's going to be a course which is I would say that this is like as prerequisites for this course. It's not very like an intensive in that sense. So you don't need to necessarily know too much about like very advanced topics to get into this course. But on the other hand, the course kind of expects a little bit of maturity in like handling a lot of notions at the same time. So as you see in the title of the course is analysis, random walks, and groups. So there will be like a lot of concepts coming together that you may have learned already in the first or second year in your studies. And it might be quite interesting, but it can be a bit challenging as well if you're used to more like studying, let's say, group and algebraic structures more, or you're more familiar with analysis and taking limits, or you're more familiar with like the notion of probability and random walks. But I hope that you can kind of meet together in this course and get some like something in the middle. And I think that how I'd like to start this lecture is maybe going into more into like a general overview of this course. You will see that because this is like an exceptional year, we'll be recording the lectures in a different way. So this will be more like several small videos on different topics, so that you can maybe go into those videos back yourself. So you don't need to necessarily watch the whole long lecture, but you can choose specific video which is more related to the topic you'd like to learn more about. So, the topic of today is basically just mainly an overview of what's happening. And so let me kind of like give you a start the beginning. So the beginning of the course will really be more about just the kind of examples where the methods of this course really apply to. Just like interesting kind of topics, like I'm going to talk about shuffling cards. Just a little in a short while, and I'm going to talk a little bit about some like applications to mutations of gene order of chromosomes. It's a bit more like a interesting topic, and then scrambling Rubik's cube, and I think I will also a little bit talk about some other more specific examples, like some random walks on circle groups and other examples. So these are like more like the examples that I like to begin from, the kind of settings where these topics apply. More broadly speaking, what they are and what kind of theorems can you expect in those fields. And then after that, I will just plan to go into the like a specific example that I want to build the whole course around into. So if you look into the lecture notes already, you can see that there will be a heavy emphasis on one single example, which is this group ZP. Let me actually write down here. So overview. So there will be the group ZP, which is kind of like the where the whole course builds around on the thing. So you don't need to necessarily know now or remember what this group is, but it's basically, we will see that it's some kind of a group of P elements, and it's like they are put around a circle. So there will be some type of a random walk on this group of P elements, where P is a natural number, at least 2. So the thing that I really want to like focus on this course is this group ZB. It's simply because it's a very simple example. It's really a place where you can do a lot of the kind of ideas, both from random walks, both from group theory, and both from analysis perspective. And a lot of the problems that we are going to see face will be much simpler in this setting initially. So usually there is a threshold in like these kind of fields when you go into this more abstract and you start to combine fields, like let's say you go to Riemannian geometry or integration theory, measure theory, and these topics, that it might be difficult to see the kind of big picture on the what is actually important within the proofs and what's actually happening. You would have to learn a lot of prerequisites for those topics. So here I'm gonna like, the purpose of this is mainly just that you can still get an idea what's actually going on, what's the interesting connections you have with these fields. And that's thanks to this group ZP. So when you look at this group and you think, oh, it's like really simple, it's like only like P elements, and it's like, why would this be like an interesting example? But it turns out that it actually does contain a lot of structure once you go into this like these bigger questions. So that's why I want to like maybe emphasize this a little bit to that this will be the kind of main thing. So as kind of like the main overview that you will see that what we will concentrate on this group ZP, it will be like we will build basically probability theory here. On the ZP. So this will be like to allow us to talk about notions like information and random walks, basically, that these topics make sense. And it's something to like that you probably have seen in some form or another. It's like probabilistic notions and other things, but I'm going to revise them here and just talk about them on this setting, that we can maybe talk about a bit more about this topic. So this is information theory. Maybe that's a better way to say it. And then, like, once you have this kind of ideas of probability theory, this will be like in the lecture notes. This is the section 2. We will go into the more like studying like this kind of let's say like time evolution within these things. So we will talk about like dynamics on ZP, which is like basic topics here is like basic evolution of random walks. So we will have like notions like convolution, mixing, and ergodicity. We see like fundamental notions in this like world of random walks and dynamics, that it's really like something that you see a lot in this theory, but we will have to like think about this more. And then after this, like this was the section 3. You will end up to topics like I will talk about harmonic analysis, which is kind of like the foundations for understanding then the behavior of these random walks and the probability theory. So the harmonic analysis basically is kind of like an introduction to Fourier series. So you will see like notions of like Fourier transform. You will also have a little bit of feeling like this L2 theory, which is kind of important to be understanding these kind of notions. So we will like the purpose of this is to basically show that when you start from these like probabilistic models like random walks and these groups like let's say this ZP, you will be able to like study those random walks using these methods of harmonic analysis. So instead of just introducing the harmonic analysis as a theoretical tool, we will actually apply it immediately. So we will apply this to the random walks, and that's kind of the purpose of section 5. So there's this let's call it the finding the mixing time, which is the section 5. And here basically we will like apply harmonic analysis to study let's say mixing of random walks on ZP. So that's kind of the main bulk of the course will be on these like five, these basically these four sections that consist all on like the group ZP in everything. So and at the end of the course, basically depending on like how much time we have and like what kind of things, but this is like really all the main examinable content, but there will be something in the final exam just a little bit on the last section, which is on more like general groups. So you have this like applying to ideas to more general groups. This is section 6. And here, for example, we will talk about this group, like this is the torus, discrete torus group that we want to talk about, and we will also talk a little bit about these kind of connections to representation theory. And then finally, we will apply ideas to card shuffling. So this is the kind of topic, the card shuffling, that I'm planning to talk about in the very beginning of the course. So the kind of, you will see in a soon that we'll talk about this idea of like shuffling cards, and then kind of having like some theorems about like how many shuffles is enough and so on. So we will try to like talk about this more at the end. So this is kind of like the purpose of this last section is to basically connect it back to the very beginning, to these more complex groups where you might want to study this field. So we will try to do the same in the end. So this is kind of like the basic structure of the course, and I will now like basically continue like in the next topics about shuffling cards. I will come into that and the other ideas.